Right, say hello, hello, hello. Can you please chat? Just double tap on the screen nicely there so that we can get the likes up there. That really helps a lot. I am going to be doing some grade 11 mathematics now. We had some good time. I think we spent some good time doing some grade 10 maths. Now it's time for grade 11. Let's tap viciously onto on the screen there so that we can get the likes up there, guys. At least let's get it up until 1,000 likes, and then we'll get going as we wait for people to join in. I don't want people to be missing out too much. Yes, and it is grade 11 that we will be looking at. Grade 11 exponents and surds. Yeah, the previous live lesson that I had, guys, covered exponents, I think, to a great deal. So I'm just going to do one more exponent question. But if you guys want to get a taste as to what I did in exponents in my previous live, you guys are more than welcome to hop onto my YouTube channel and check out the lessons done on exponents. I feel like when it comes to simplifying exponents, you guys now should be at a place where you are like, well, sir, I think you did justice for where that is concerned. All right. And this is just a little bit of a sort of like a preview as to the YouTube channel that I have. These were the lessons that I had actually done during festive season. All right. So you guys then should see there. The most recent upload was a grade 10 algebraic expression with products. Today I did factorization, so that will be uploaded later on in the day. But grade 10 algebraic expressions, if you go to my YouTube channel, link is in my bio. That's what's there at the moment. Grade 12 sequence and series, we've done 3 parts of sequence and series. Part 1, part 2, part 3 is all there on the YouTube channel. Have laws of exponents for grade 11 that we've done also previously, so you guys can check that out. So there's just a lot to check out there on the YouTube channel, you know. And you go further down the YouTube channel, there's yeah, that entire variety of things that we did in December. So December 2025 was not a month that we were chilled. We were working, we were busy, we were joining live sessions, some of us, you know. Yeah, so please guys, check this out. Check the YouTube channel. The link is in my bio. The link to the YouTube channel is in my bio. So if you want to check that out, please hop on there and familiarize yourself with what is actually there. And I would really encourage you, despite the video quality, because these are videos that I'm literally taking from the live lesson, I'm uploading them as they are. So the videos are very phone compatible, because if you're using your phone, you should be able to view the video quite nicely on your phone, because yeah, I'm taking the video live using the phone. So it is as thin, if you will, as you see it on the phone. You can really watch the entire video and watch these videos in segments, right? I apologize that in much of the videos there's a lot of talking. I talk a lot, things that are not even related to what I'm teaching, but at the end of the day, yeah, it's because there's interaction during my live lesson. So guys, please check that out. Check out the YouTube. Like I said, the link is in my bio. Check out the videos, watch the videos. If you want to catch up as much as you can, and make sure that you are not being left behind. The syllabus for the year is uploaded there. You can see, guys, there. I'm showing you more of what I've done. Okay. Grade 10, you know, your interval notation. Grade 10 set builder notation. Those were actual videos that I took. They're not live lesson, but it's actual videos I took of what interval notation is and the difference between interval notation and set builder notation. Yeah, you know, because I'm trying to make sure that the content for grade 10 is complete, 11 hopefully as well, and 12, so that when you come to these videos and you watch them, you can actually gain a lot, and you can start really early for yourself. Okay, I think let me remove these and let's get down to business. Let's get down to business. All right. Okay, so I said, guys, I'm just going to do one exponential equation, one exponential expression question. The laws, you know, these are all the things that we had done from these other live lessons. Like I said, if you check out the videos there, you will be able to benefit. Let's just do one more exponential expression type question. We have 5 to the power x plus 2 minus 5 to the power x minus 1 over 2 times 5 to the power x. Please continue to double tap on the screen, share the live with other potential friends, families, neighbors, your dog, your cats, your uncles, your aunties. Let's harass people, guys, with the fact that we are starting early with mathematics so that people can become positively affected, if you know what I mean. Okay, 5 to the power x plus 2 minus 5 to the power x minus 1 over 2 times 5 to the power x. So we established a way to work through questions like this, and that is, first and foremost, we look at the entire thing. We have one expression, one term. In the numerator, we've got 2 terms. In the denominator, we have 1 term. But in the numerator, there's something that we observe from the expression in the numerator. And what is that? We observe a minus sign. When we have a minus sign, it means law number 1 and 2 is basically out of the picture. The minute there's a plus and a minus sign between bases, guys, law number 1 and 2 are out of the picture. In other words, we are not even going to be thinking of this law and this law. They are not going to be working at this present moment as we start the questions. Okay, so what we then do is we are going to look at the top. We look at our first term minus the second term. And what do? We split, right? The first and the second term. We split it using the reverse of law number 1 of exponents. Also, guys, what we observe is that base 5 is prime and this base 5 is prime. The exponent x for this 5 has a coefficient of 1, as well as the base 5 for this x has a coefficient of 1. So that is actually a good omen. That means something is good. So what we do then is we split 5 to the power x and 5 to the power 2. Then we split 5 to the power x times 5 to the power negative 1. The denominator is already split. Okay, so after splitting, we observe again in the numerator what type of factorization can be applied in the numerator, because there's a minus sign. So that's where I said, guys, after splitting, you then factorize. Obviously, there's a type of factorization to be applied. Whether in this case, as you can see, it's common factor factorization, or in the situation where the base would have been raised to the exponent 2x and then this one 1x, we would take into consideration another type of factorization, which is quadratic trinomial factorization. So the whole thing here is that we need to split then factorize whenever we see that there's a plus and a minus sign between the exponential bases. When we take out the coefficient 5, the common factor 5 to the power x, what gets left behind inside is 5 to the power 2, and then minus on the other side, we get left with 5 to the power negative 1. That will be all over 2 times 5 to the power x. Now remember, in the numerator we had 2 terms initially, but when we factorize the numerator, now in the numerator we don't have 2 terms, but we have what? in the numerator. Because we've factorized in the numerator and we've taken out a common factor, we now have how many terms in the numerator? That's my question, before we get down to business to the answer. Thank you, Chloe. We now have one term. We now officially have one term, which is beautiful. All right, which is so beautiful. We now have one term. So if we have one term, we then go ahead and we ensure that this divided by that, because the 5 to the power x and the 5 to the power x in the numerator and the denominator are not across an addition or a subtraction sign. Like for instance here, the 5 to the power x was across an addition and a subtraction sign because they are separate terms. Here, the 5 to the power x is a common factor. Its relationship with the bracket is one of multiplication, and this 5 to the power x in the denominator is a relationship with the 2 of multiplication. So cancellation to simplify is possible. Then we are left with 5 to the power 2, which is 25, minus 5 to the power 1 over 5. Sorry, 5 to the power negative 1 is 1 over 5. Over what? Over 2. Simply grab your calculator. We can punch all of this in the numerator within our calculator and just get what the answer is there for our numerator value. We have 124 over 5. 124 over 5 divided by what? By 2. Then 124 divided by 5, we divide that by 2. The answer, we should be able to get an answer, as has been indicated earlier on by someone, of 62 over 5. Right, and that is that. Finished, complete, simplifying an exponential expression where we clearly have subtraction with division and multiplication in the mix. All right, so we split, factorize, cancel if possible common things in the numerator and the denominator. Then obviously we then apply basic simplification. This is 25 minus 5 to the power negative 1 is 1 over 5. 2 times, this here cancelled. Remember, when we cancel, we are left with 1 and 1. 2 times 1 in the denominator is 2. Then, of course, 25 minus 1 over 5. In your calculator, you get 124 over 5. You divide that by 2. That gives you an answer of 62 over 5. And that's complete. So, guys, that basically then kills or completes the aspect of simplification of exponential expressions for now. We are now going to enter into the world of surds and roots, because when you do exponents, you don't only look at exponents, right? Meaning, by exponent you mean a base with an exponent. Now we are going to look at surds and roots. Okay? Yeah. Now by surds specifically, guys, a surd is simply an irrational number. That is what a surd is. For instance, the square root of 2 opposed to the square root of 25. All right. From these two, which one is a surd? Square root of 25 and the square root of 2. All right. Now, like I said, a surd is an irrational number. What is an irrational number? An irrational number is a number that cannot be written as a fraction where the numerator and the denominator are integers and where the denominator cannot be 0. Your decimals of surds are non-recurring and non-terminating. Non-recurring and non-terminating. So between the square root of 2 and the square root of 25, our surd is the square root of 2. Square root of 25 can be simplified. It is equal to 5, which is not irrational but rational, because 5 can be written as a fraction where the numerator and the denominator are both integers and where the denominator is not 0. So that's why we maintain that a surd is an irrational number. Okay? And usually when they say in a question, leave your answer in surd form, they are in essence saying that you must leave your answer having a what? A root. A root. A what? A root. So this is what we call root form. This here, okay, though this is a surd is written in root form. Hey, I hope you are hearing me here. So what did I say initially? What is a surd? A surd is an irrational number. Ne? Then I said to you, our surd is written in which form? In root form. So for instance here, what do we have? A square root. What is this? It is a cube root. Okay? Does that make sense? So guys, if they say leave answer in said form, it means they don't want any decimals as your final answer. Also secondly, if you are simplifying something of this nature, you cannot use a calculator. So when they ask you to simplify surds, they will usually say to you, without using a calculator. Now guys, the minute you begin to express an answer as a decimal number, what does that mean? It means you used the calculator at some point. So we want to avoid that. We want to avoid expressing our answer as decimals. 2, we also want to make sure that we understand that when they say without using a calculator, they are saying you must show your steps that you took step by step. I want you to walk me through each step that you took in getting to the answer. That's what without using a calculator means. Without using a calculator means I want you to show step by step how you got to the answer. It does not actually mean don't use the calculator. It doesn't mean don't touch a calculator. That without using a calculator does not mean don't touch a calculator and you may not necessarily maybe punch something there and there, but it says show step by step how you got to the answer. That's what without using a calculator means. So just to go back to Tlochi's question, what if you continue simplifying the surd? Will they penalize a mark? Remember, the surd must be simplified completely and fully, right? But it must not appear as a decimal number. That's what you need to avoid more than anything else. Okay? Yeah. If they say leave it in surd form, you leave it in surd form. All right? And that's very important. So very quickly, I want to look. Yeah, when they state that leave your answer in surd form, you must leave it in surd form. You cannot go further. All right? Yes. So you are 100% sure. Gogetso 66. Schools are closed. Yes, Gogetso, schools are closed, but our minds are not closed. They are open, more especially because it's 2026 and it's a new year. Our minds are that much more opened because we are cognizant of the fact that in no time, things will be starting. And Tina, we have goals. Maths, we want to actually attain something in the range of 95% to 100% for mathematics. So if that is the case, my dear Koketso, there is no ways that me is going to start the normal way. If you want things to turn out differently in life, you must do something that you've never done before. If you want things to turn out differently in life, you must do something that you've never done before. Because if you do what you've always done, you will get what you've always got. That's the bottom line. All right? So hopefully that's a mouthful for you, Koketso. So let's look at some things here. 1. Multiplication, guys. Multiplication. When we multiply, we can, if the roots are the same. This is a square root, this is a square root. That means I can then combine the multiplication of what is inside the different roots underneath the one single root. So multiplication, we can combine the multiplication of the values inside the roots, as long as the roots are the same. Key square root. Therefore, we can multiply underneath, as is the case here. That's for multiplication. 2. What about division? Well, we can, as long as it is square root, we can divide house both of them inside the square root. Okay. 3. Then you ask me, what about, say, addition? My dear beloved friend, Jamoni, Happy New Year, sir. Happy New Year to you too. Give yourself a break. No. I did give myself a little bit of a break, Jamoni, but at the moment, we are just we are doing something that we've never done before because we want a different outcome. So, sorry. Square root of A plus the square root of B. We call these guys unlike terms. So the square root of A plus B is equal indeed still to the square root of A plus the square root of B. No combination happening. We do not combine the addition of A and B underneath the same root. We do not. So this does not just apply for addition alone. It also applies for subtraction. Do you feel me, my brothers and sisters? I hope you feel me there. I hope you feel me, because I've got a feeling that when we feel, then something happens. All right? 4. Let us look at this particular situation. The square root of A plus the square root of A. What is the difference between this and that? We said this stays separate because we call these what? Unlike terms. What can we say about this? Square root of A plus the square root of A. We call these what? What are these, guys? Bam 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 baram bam baram bam 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 bam. Bam baram bam bam. Thank you, Elias. Thank you, Ngoto. These are like terms. So therefore, what would be the outcome there? What would be the outcome? When we are dealing with like terms, what do we do? Be careful, Olwetu. Be careful, Mr. Olwetu Mota. Be careful, my brother. That's a very dangerous answer there, Olwetu. Square root of a plus square root of a. We keep the variable with its root, and then we add the coefficient. Okay, let's be very careful with this one. We keep the variable with its root, square root a plus square root a. We keep the variable with the same root, because what makes this like terms is the fact that this is a, so the variables are the same. The roots are the same as well. That's why we call these like terms. The variable and root must be the same. If the roots are not the same but the variables are the same, we cannot add those because those would still be called unlike terms. Okay, I hope you understand. Mr. Self-Mastery, it is literally the first day of the year, taking a break from stressing. You have a mindset that is completely wrong, my dear friend. We are not stressing when we come and we take care of things early. We are actually taking care that we do not make it a stressful situation when we begin to start early to address things that we know are up and coming. We don't want to impose unnecessary pressure on ourselves when the things get thick and there's other subjects to take care of. In this space, we can look at maths alone, early. That takes care of stress. So people need to change the way they think. You know, thinking is, that's why if some people comment a certain way, it's because they are thinking in a certain way and then their thinking is off. So the variable, guys, and the root together must be the same in order for it to qualify as a like term. Okay. Then what do? We keep the variable with the root. Then we add the what? The coefficient. Who is here? It's 1. Who is there? It is 1. We add the coefficients. We keep the variable and the root that way. So the answer is 2 root a. Okay. So the variable and the root must be the same so that it qualifies as a what? Like term. Please, my people. Please, my people. Please, my people. Understand these things. Okay? The answer cannot be a squared. Yeah, because we are adding. No? Look at this one. Look at this. Look at this, for instance. The square root of a plus the cube root of a. Let me check with you. Are these like terms, guys? Are these like terms? Can we call them like terms? Can I apply the same logic as I applied there at the top? Okay. If you are saying no, they are not like terms, why are you saying they are not like terms? I want your comment. If you are saying yes, they are like terms, I want you to know why are you saying yes, they are like terms. I want your comment in the comment section. Okay. Because you will remember I spoke about a condition that makes terms like or unlike if we are talking about the roots. Okay, who needs to be the same in order for it to in order for us to regard it as like terms? Who needs to be the same? The variable must be the same, but additionally the root, in other words, if it's the square root here, it must be the square root there. Now Ngwato is saying nope, these are not like terms, and in the comment that follows that one, he is then saying they are not the same. All right, and I hope we Ngwato understands why he is saying they are not the same. Very critical. Very critical. Even better reason for us to do this, because it is the new year, God's angel. When you are God's angel, but you are here acting as the angel that is in opposition to God's angel, you are wanting to use the excuse of it being a new year for people to not newly start afresh and start early. Yeah, whose angel are you then? Opposing. Anyways, guys, square root of a plus the cube root of a, guys. These are not the same. Why? The variable is both a and a, yes. But what about the root? This is the square root. This is the cube root. Are the roots the same? No. Roots are not the same. So if the roots are deviating, then it means all in all, these are unlike terms. Guys, these are unlike. Hey, entate. These are unlike terms. This is a cube root. This is a square root. So these are unlike terms. And guys, unlike terms, this is the answer. Square root of a plus the cube root of a is equal to the square root of a plus the cube root of a. It stays as it is. Get with the game. The variable as well as the root must be the same for it to qualify as a like term. Like here, this is the square root and this is the square root. This is a. Variable and root the same means like term. Variable not the same, variable the same, but the roots different, unlike terms. Entate. Hey, bana. Hey, can I live without regret, TikTok? Oh, my soul. Look at this one. This one we've already taken care of. You know, we already said most. This one is also unlike term. So I think we get the picture, guys. Okay, what makes it qualify as like term is if we have the same variable inside the root and the same root. Please, guys, cube root and square root are not the same. Fourth root and eighth root are not the same. Cube root and the 12th root are not the same. You guys must know what is the same and what is not. By so doing, my beautiful people, you will have accomplished a lot. So please, guys, don't take what I'm writing here for granted. What am I saying? Do not take what I am doing what I am writing here for what? For granted. All right? But now someone is asking, say cube root times say square root times cube root. Okay? So okay, let us explore what you are saying. Let's say now we are multiplying a cube root and you're multiplying, not multiplying. Okay, so let's just rewrite this. Sorry guys, sorry. Okay, there we are. So with this one, how in the world do we do or take care of Mr. Square root of A times the cube root of A? In other words, you see here we had the same root. We were multiplying. We had different variables. And then when we actually were taking care of this, what did we do? We actually kept the root. We multiplied what was different. Okay, we multiplied what was different. Now the question is being asked here, if we have the square root of A times the cube root of A, what would be our approach to this? So me being the person that I am going to give this and hand it over to the floor. What do you guys think? What do you think? What do you guys think? Come on, comment section is there for you to answer. What do y'all think? Scrutinize. Look at scrutinize. Guys, do you see what scrutinize is saying there? Okay, are you scrutinizing what scrutinize is saying there? Scrutinize is scrutinizing. Okay, guys, we are simplifying here. All right, simplifying. We are doing what? Simplifying. I hope we understand this. Okay, simplifying. That's what we are doing. Yeah, so what I love is the fact that since we have a multiplication and it's of what? Of different bases. Okay, I love what scrutinizer said. There's something that you guys need to know how to do as well, which is how to convert a root to rational exponent. Okay, how to convert a root to rational exponent. So if you want to know how to do that, guys, it's simple. If you have the nth root of, let's say, x to the power m. Okay, I think I did this in the previous live as well. The nth root of x to the power m can be written as x to the power, we remove the root and we say m over n. Are we together? We remove, what do we remove? We remove the root, and to convert the root to a rational exponent, we can write it as x to the power what? M over n. Are you feeling me there, guys? Are we together here? Just take it in a moment, because this is important. All right, this is a rule you should have known from grade, you know, whenever you have a root form x to the power m raised to a nth root, the nth root of x to the power m, you can rewrite x to the power m with the nth root as this m belongs to the numerator for your rational. And the reason why we say rational exponent is because a rational number is a number that can be written as a fraction. So the numerator is your m. The n that is here is your denominator, and then the root is removed. So in other words, if you ask yourself, what is the square root of x, for instance? The square root of x is simply written in rational form, rational exponent form, as x to the power. What exponent is here? It's 1. And then since it's the square root, guys, what is the number that we don't see that is there? Guys, square root means there's a 2 square root. That's what it means. So it's 1 over 2. So it's x to the power half. What if we had the cube root of x? That is simply x to the power 1 over 3. Okay. So guys, this is around what we need to know when it comes to the laws of roots and surds. When we know these things, guys, okay, when we know these things, then we can be able to do what is right. Okay, I think Hayden is definitely not spamming. Hayden is just answering the correct things. What is this? Stop spamming my foot. Get off Hayden's back. Please, get off Hayden's back. Get off Hayden's back. Okay, all right. Hopefully that's clear. So if you come back to this problem, using the fact that we know what rational exponents are, this is a to the power 1 over 2 times a to the power 1 over 3. When we have things in this form, that means we have the answer in exponential form. So therefore we can do what, guys? We can keep the base, add the exponents. You can grab your calculator and just write a to the power. Obviously, it's going to be 5 over 6. I know some people play the butterfly game. 3 times 1 is 3 in the numerator. 2 times 1 is 2 in the numerator. 3 plus 2 is 5 in the numerator. And then you just multiply what's in the denominator. 2 times 3, that is 6. So your answer is 5 over 6. That's basically how you add 2 fractions that are together. All right. Or, like I said, guys, Mr. Calculator is forever there. And if you do it this way, that's also fine, really and truly, because at this stage, this is the resource is available for that very reason. So for us to move from here to the answer, that's 100% fine. If they insist, leave your answer in surd form, of course, now you can revert back to surd form and write what? Root form. You can write it as the 6th root of a to the power 5. Okay, so there's always a way, guys, to maneuver around situations and problems that we are basically having. Okay, and then there's this guy that is very common. We sometimes get something like this, and then there'll be something like that, and then let's say there's 3 here, and then there's something like this, and then they say to you, simplify this thing, and you look at it and you're like, huh? What ring? Okay, let's just put A, B, and C so that we can value the general input. Okay, let's just say we had this the B root of x, and it's covered by the A root, and it's all covered by the C root. Okay, so then how do we express this in a simpler form? All right, guys, the way we express this in a simpler form, okay, I hear what you are saying, Ngwado, but the rule, it's just straightforward. Okay, I see you as well, scrutinize. The rule is always start from the inside, it unwinds. I see you there as well. But guys, right, we can simply do this. This B, we multiply with this A, we multiply with this C. So basically you get one root where you are multiplying all of this. In other words, it's going to be C times A. All right, let me just write it a bit bigger here. That will be C times A times B. So whatever that outcome is becomes your new root. And that's all going to be under the x. Because you guys get so many problems like this, all right, and many of you are unable to answer those questions because it's like the rule is not, you're not familiar with the rule. So if you have a situation where there's a variable and it's housed under different roots, all you do is you multiply the values of those roots, guys. All you do is you just multiply them and you get the new root, okay, with that variable underneath. And if they say express that answer in exponential form, of course, you know how to change a root form so that it is in exponential form. You know what to do. You know exactly what needs to be done because you have the rule that can help you. Okay, makes sense? Yeah. Please, my good people, let us make sure that we know these, I would call them hacks if you want, or rules or laws. If you're playing a game, that's why I call this channel MATHSISAGAME. If you are playing a game, okay, and you don't know the rules, it sucks playing the game, doesn't it? But the minute you know the rules of how to play the game and you apply the rules consistently as you play that game, don't you get better and better at playing the game? And subsequently, don't you just become a pro at playing that game? You do, don't you? So MATHSISAGAME, guys, it needs people to know very well what the rules and the laws are. Then those people need to go and search for problems and apply the rules and laws consistently, especially the minute they know what is supposed to be done in a particular problem. You apply those rules and laws consistently over and over again, and then you become a pro. And then, do you know what, guys? Do you know what is the result of that? This becomes a reality. Getting 95% to 100% for mathematics. This becomes a reality for your life. Okay? So grade 11s, I plead with you, let's take that one step at a time. Chloe, I see your question there, but I will not be doing that right now because I'm busy with grade 11. And when you are coming here asking me to do long division, that long division that you are asking me to do, send me a DM message, all right? And I will be sure to make it a point that in a lesson relevant to your grade, what grade are you in? I can address that particular question. Just make sure you follow me. If you are grade 10, 11, and 12, and you are pure math student, follow me on this channel so that when I have live lessons, I will consider the question that you have asked and then address that at that time. Okay, I'm going live for grade 12 tonight at 9 p.m. after 9 p.m. tonight. Grade 12 is always at night. We are night babies. Okay, and today we are starting functions because we are done with sequence and series. Okay, so even that question you're asking me to do simultaneous equations. What grade are you in? If you're in grade 11 or 12, you want me to do simultaneous equation, that time will come. Right now, I'm busy with exponents for grade 11. So, in fact, specifically surds. Let's look at this question, guys. This question says, simplify without using Mr. Calculator. Okay? Simplify without using Mr. Calculator. Addition and subtraction serve for the roots I've already covered. So now you are taking me back. I've already done addition and subtraction, sir. Who is this person? The one who's saying addition and subtraction with the question marks, many question marks there. Yeah, addition and subtraction of surds and roots we've looked at. Okay, so I'm just going to do these questions and I'm going to refer back to the notes for that. Okay, so that means you came in a bit late for this live. That's why you're asking me this question you're asking me. Simplify without using a calculator. We have 2 square root of 150 minus square root of 24 over square root of 12. Okay, guys, this is really, really nice. Depending on who's doing the question, I think there are 2 viable methods we can use when doing these questions. So I'm going to look at both. All right, let's first look at this method. 2, we are good with it. 150, let us grab our calculator and actually convert this 150, which is a composite number, and convert it to prime base by applying what we call as prime base factorization. Calculator helps us out very nicely with that. All we do is we take 150, we say equal, we press shift button there, which allows us to select all the yellow things in the calculator. When you press shift, guys, that allows you to select that guy, select that one, the cube root, select that guy, select that one, select that one, select that one, select that one, and so it goes. So remember, what did I say? I said 150, I press equal, I press shift, then I press Mr. Fact. There we have it. We have 2 times 3 times 5 squared. 5 squared is a perfect square. Fits in very nicely because this is a square root. 5 squared times 2 times 3. So what I'm going to do, 2 into 2 times 3 times 5 squared. Okay, we fine? Minus, do the same thing with 24. Grab the calculator, 24. Okay, 24. I say equal, shift, Mr. Factor. There it is. 2 to the power 3 times what? 3. All right. Bit different here because the multiplication of these two, I don't have what I would refer to as a perfect square in the mix. So I'm just going to look at this, okay, and think of other multiplication, other products for 24. What else do I have for 24, guys? If you look at the factors of 24, 12 times 2 is 24, but 12 and 2 are both not perfect squares. So I leave that. I go to another one. What about 8 times 3? 8 times 3 we just looked at here in the calculator. No perfect square there because we have a square root. We would want to have a perfect square underneath the root. What other product, guys, do we have of factors that will give me 24? Comment section. Now you need to go ablaze. Help me out. What other factors of 24? Okay. I need the factors of 24, guys. Factors of 24. I need them. Give them to me. Okay. A product of factors that will basically give me a perfect square and another number. Ngwato in the comment section. W's to Ngwato. W's in the chat for Ngwato. Ngwato gives me 2 squared times 4. Ngwato, you are the real deal. So for your 24, guys, you have 12 times 2. Okay, you have 8 times 3, you have 6 times 4. Why do I know this? It's because when I talk about the factors of 24, you see, me knows all the factors, because when I was doing grade 8 and 9, I was a pro. Now in grade 11, it's like there's nothing that goes past me. Does that make sense? Nothing goes past me. I upload all the live lessons that I'm done with when I finish onto the YouTube channel. So you can, when I'm done with this live, you can check out the YouTube channel and you can watch the live lesson there. Okay. I will upload it later on during the day. Both the grade 10 lesson I did earlier on and the grade 11 lesson that I'm busy with now. So the video is there to watch when you are ready to watch it. You can also watch the previous videos I've done for exponents on grades 8, 9, 10, 11. All right. So 1 and 24 could be a choice, but no, that doesn't work here. 2 and 12 could be a choice, doesn't work there. 3 and 8, no. 6 and 4. Okay, 6 and 4 works. Link is in my bio, Melokush. Okay, so that's why I choose here 2 squared times 6. Hey, moving right along. A perfect square and another number. A perfect square. This 2 times 3 is also going to give me what? The 6. You see, a perfect square and another number. A perfect square and another number. So this perfect square and another number, the combination of a PS and another number. I'm just going to use A, guys, to designate another number. This is the combination I need inside there. Because this is a square root, I'm interested in a perfect square and another number. If it was a cube root, I would be interested in a perfect cube and another number. But at the moment, I'm interested because it's a square root. I need a perfect square and just another number. Because it's a square root, a perfect square, and another number. Now we go to 12. I'm sure you guys already in your heads have an idea. What perfect square and another number combination of factors can I write down for 12? Sometimes the calculator helps, sometimes it doesn't. 12 is equal to shift, boom, 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 fact, boom. 2 squared times 3. Perfect square? Yes. Another number? Yes. So let's go. 2 squared times 3. Right? Right, let's go. Let's move now. I think we have room to move. If you look at what is in here, maybe just make it concise. We are going to write this as 6 times 25. All right, which would be my other method. Guys, really and truly, I wasn't going to express these in exponential form for the other method. For the other method, I was going to go directly to the 2 numbers where there's a perfect square and another number. So 150 is 25 times 6. That's the perfect square and another number. 24 is going to be 4 times 6. Perfect square and another number. In the denominator, 12 is going to be 4 times 3. That's the perfect square and another number. So we need to get into the groove of a perfect square and another number if we are given a square root. But if we are given a cube root, we go to the idea of a perfect cube and another number. All right? Okay, let's move. 2 stays. We can split this. Why can we split this? According to the law of roots, a times b underneath the square root, we can write as square root of a times the square root of b. So let's split that. Square root of 25 and square root of 6. Square root of 4 times the square root of 6. All right. Square root of 4 times the square root of 3. Then, what's the square root of 25? It's 5. 2 times 5 root 6. Square root of 4. 2 root 6. Square root of 4, 2 root 3. Board mess. 2 times 5 is 10. Snoko. 2 times 5 is 10. Okay. Those people who have been grooving with that song, I don't understand why you wouldn't want to be doing maths. But already the festive season songs were leading you towards maths. 1 plus 1 is 2. Snoko. Come on, guys. Really? Square root of 6 minus 2 square root of 6 over 2 root 3. Guys, I'm just dragging this out, this problem, because I want you to see every step that I am basically taking. All right, this is for explanation purposes. There's definitely steps here that I wouldn't write if I'm actually answering the question, but I'm writing out all the steps so that you guys can see exactly what I'm doing. And I'm expecting you guys in the comment section, if you are lost somewhere, to not wait until I'm done at the end and then ask me the question, because that's going to drive me bananas. You see this B, it's for brackets, but it's also for driving someone bananas. This D, driving me bananas. D, driving. B, bananas. Or M, mad. So I need you to tell me if you guys are good. Yeah, or if there's any questions so far. In the numerator, there are two terms. These terms are like terms. Why do we say these are like terms in the numerator? Why, guys? We say these are like terms in the numerator. Why? Why do we say they are like terms in the numerator? Yes, exactly. The root is the square root. The number is 6. So the roots are exactly the same. And the numbers inside the root are the same. So we say they are the same. Like terms. So what do we do when we are dealing with like terms? So in the numerator, can we subtract? Yes. Okay. We can subtract in the numerator. We can subtract in the numerator. We keep the root. So it's root 6. Then we add and subtract the coefficients. What's 10 minus 2? So what will be the number before the root there? Okay, so we are exactly applying this when the roots and what is inside is the same. Then what do? We keep the root, then we add the coefficients. So 1 plus 1 is 2, snorkel. 10 minus 2 is 8 over, we have a 2 and a root 3. I'm sure you guys can see the simplification from here. The relationship we have now is 8 multiplied to this and 2 multiplied to that. Okay? Go back to the rules. Okay? I see a square root and a square root, numerator and denominator, which means what? The 8 divided by 2 will take care of itself. But the root 6 will be written as root 6 over 3, the entire thing. Outside, what's 8 divided by 2? It's 4. 6 divided by 3, inside there will give us what? 4 root 2. Do you see this, guys? Do you see this? 8 divided by 2 in the simplification of 8 divided by 2 goes into 8 how many times? 4 times. So our answer is 4 over 1 for the number before the roots. The root of 6 and the root of 3 have a relationship of division. The roots are the same. They are currently split. But can't I combine these two using this particular rule? Yes, I can. So therefore, I have root 6 over root 3, which is written as the in root, which is the same, 6 over 3. What's 6 divided by 3? That means the root is 2. So the final answer then is 4 root 2, grade 11s. Okay? Someone there in the comment section is saying grade 8. The thing is, the reason why that person is saying grade 8 is because that person knows that this, from this step, from here, this is a typical simplification question for a grade 8 learner. From here, this step onwards is a simple simplification question for grade 8s, because they learn these rules in grade 8. If you did not learn them in grade 8, or you were too immature when you were in grade 8 and you did not really care that much because you were still a child, well, maths is coming now to bite you because you were too immature. So now you need to mature and wise up. All right? Please, guys, don't let this idea of you being here doing maths so early go in vain. It will really break my heart if some of you are just here, you are listening, you are having a good time, you are watching, but none of this is actually helping you, or it's going in. You know, and and you know what, you are just going to be the same like all those kids that were having a hell of a good time during the holiday and were enjoying, but when you were busy here on my live watching, but you still get the same old boring marks that are weak whack. Aye, guys, we can't do that. So please pay attention, take note of these rules and these laws that I have explained here. All right, and make sure that you have internalized them for yourself. Okay, yeah, so that's how we answer that question. Okay, let me just go back again. What happened? This is 2 root 150 minus the square root of 24 over the square root of 12. What do we see in this expression? This is actually one term. All of it is one term. Why? Because the division line makes it one term. In the numerator, how many terms do we have? We have 1 minus separates 2, then over 1 denominator. So what we first do when we are approaching these questions, because we have a square root, we are interested that inside the square root, we get a product. By product, I mean a multiplication of a perfect square and another number. So 150 needs to be broken down into a multiplication or product of a perfect square number and another number. So when we prime factorize using the calculator, 150 is equal to shift fact gives us 2 times 3 times 5 squared. 5 squared is obviously a perfect square. So our perfect square number is going to be 25, because 5 squared is 25. The other number is 2 times 3, which is 6. So 25 times 6 is a combination of a product of a perfect square, 25, and another number, 6. And is that fine for this situation? Yes, because we have a square root here. That's why we look for a perfect square and another number. If it was a cube root that was here, we wouldn't look for a perfect square and another number. We'd look for a perfect cube and another number. So we always align the product of the two numbers, the one number being in accordance to the root. And then we don't care about the other number. It doesn't have to really comply to anything. So we always have to have a product of a, if it's a square root, perfect square and another number. If it's a cube root, perfect cube and another number. If it's a fourth root, then it means we need to get that sort of perfect something, which will basically work underneath that root. Okay, and another number. So here, 6 times 25 works for 150. 24, 4 times 6. That works there. 12, 4 times 3. That works there. Perfect square and another number. Perfect square and another number. Perfect square and another number. Now I can hear some people saying in their heads, sir, what is a perfect square? What are you talking about? Guys, what are perfect square numbers? Any grade 8 learner will tell you that a perfect square number is numbers like this. 1, 4, 9, 16, 25, 36. What is special about these numbers? Well, the way that they are formed is they are formed by multiplying themselves by themselves. As a result, anything that is formed by multiplying itself by itself, it means it's perfect. Imagine if you could make yourself perfect like God by yourself, then it would mean you are perfect. But unfortunately, you are not. You know you are imperfect and you mess up every single day. So that in and of itself tells you you are not a perfect square. In fact, you are not a perfect person. So a perfect square number is formed by multiplying itself by multiplying another number by itself to get basically itself. All right. 4, it takes 2 and multiplies by itself to get 4. This is a perfect square number. 9, the same. 16, the same. 25, the same. 36, the same. Grade 8s and 9s were supposed to know all perfect square numbers up until 100. But if you are someone who's serious, you will know all perfect square numbers all the way to as much as and as far as you can go off the top of your head, so that you can know things, people. Okay? People perish. Why? No knowledge. But the minute people have knowledge, then they stop perishing. And when they stop perishing, they prosper. You see? So please, let's start prospering. This is our year. 2026 is our year. We are going to make serious moves this year and attain serious marks this year. Okay. All right. Any questions, guys? Then you see from there, after doing the PS times another number, we then do what? We apply the laws, guys. Okay. We simplify. We split. Okay. Because we can split a square root if there's multiplication. Splitting a square root when there's multiplication is possible. Then we get 5 for the square root of 25. Square root of 6 stays underneath the square root. Why does it stay underneath the square root? It's because Galoko, it is an irrational number. So it must stay there. It's an irrational number. It's a surd. It stays. 2, square root of 4 is 2. But square root of 6 stays underneath the square root. It's an irrational number. Square root of 4 is 2. Square root of 3, it stays. Why? It's a surd. It's an irrational number. Then what's 2 times 5? It's 10. Then there's that 2. You see at the top, after applying multiplication, then you now can apply subtraction, because BODMAS says you start with multiplication, then you can go ahead with subtraction. 2 times 5 is 10. Then you can subtract the like terms. They are like terms because this law allows us to add and subtract like terms. The root are the same. These are both square roots. And then the numbers inside are the same. So that means these are like terms. You treat them as like terms. You keep the root 6. You add or subtract the coefficients 10 minus 2, which is 8. The bottom you have 2 root 3. Then you can simplify from there. 8 divided by 2 is 4. This, you can apply the law. They are underneath the same root. If the roots are divided, you can write them both underneath the same root that you have. So that's why we say the square root of 6 over 3 gives us the square root of 2. So the answer is 4 root 2. Any questions before I move on to the next question? Surds and roots are simplified this way. When we have different operations, divide and subtract, we can simplify our surd in this way. Okay. No using it. We don't write this as a decimal number. We leave it like this. Okay. As 4 root 2. Okay. In the chat, there's no questions. It seems like people are fine. It seems like people are fine. People know everything. Sir is teaching very well, and people are like, Sir, just we want to go to school already and just bring home the distinctions. This is easy peasy. Never seen anything so easy. Yeah, can move on to the next problem. Just tell me in the comment section next. If I can get next in the comment section, I'll move on to the next problem that involves surds, because we are now in the Pagati inside in surds and roots. Okay, next it is. Please guys, continue to double tap on the screen. We need to get to 10k likes there so that we can harass more people. The more this live is liked, the more double taps we have there, the more people are able to, if possible, support the live creator by gifting, whether it be a heart, me, rose, anything, guys, that is able, then FYP page is ours, and we can have more people sent our way so that they can see that, hey, we are busy, and they need to also be busy. Right, let's look at the next problem. The cube root, the square root of 300 minus 147 times the square root of 27. So once again, this time round there's no division, but there's only subtraction and addition. But what do we see? Underneath the cube root, the square root, we have 300. It's a composite number. Underneath the square root, 147. Underneath the square root, 27. So we need a product. Okay, so our calculator is very helpful just to sort of like help us break the ice. Maybe in our heads we already know, we're like, we know, I think I know what we can do with this one. Maybe off by the top of your head, you know the product of factors, a perfect square number and another number to form 300. Let's see, maybe we don't need the calculator and maybe we don't need it. What about 300, guys? Tell me the product of a perfect square number and another number that I would write down that will give me 300. The perfect square number is what? Let me give you guys a chance to tell me for 300. Let's just focus on 300. We'll focus on the others. Let's do one square root at a time. One square root at a time. So the perfect square number, the product of perfect square numbers that we are going to utilize for 300 is perfect square number and another number. Makeba, 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 wena wendlovu. Makeba. Oh, Makeba, kunzmalanga. Okay, 100 times 3. Makeba there has done the things. All right, now for those that use their calculator, they would have said, right, 300 is equal to, and then said shift, then said fact, and they would have gotten 2 squared times 3 times 5 squared. So what you would have noticed then is that that 2 squared and that 5 squared, those are both perfect squares. And you can actually multiply these perfect squares. They will give you another perfect square. So 2 squared is what? It's 4. And 5 squared is what? Is 25. 25 times 4, what does it give you guys? That 100. So that's where that 100 times the what? The 3, which is the other number. Okay? So I hope we kind of like see this. Okay? I hope we can see this nicely as it prevails, but it would have been very fine for you to actually use 3 is equal to shift fact. So thank you so much for the comment section being ablaze like that. I really appreciate it, and I hope you can see, all right, what we have done there. Okay, that would have also been perfectly fine. All right, someone else who's doing this question could have said 2 squared times 3 times 5 squared, which is also fine. No problem. So I'm just going to do these simultaneously. 100 times 3 opposed to that. Let's move on to 147. What about 147, guys? 147. What do we have in there? What do we have in there? Oh, Tlochi, W is in the chat for Tlochi. 3 times 49, right? 3 times 49. And indeed, guys, 49 times 3 does give us 147. So I'm going to write down that 49 times 3. Then let's just go to the calculator and say 147 is equal to, and then we say shift. Where's the shift button? And then say fact. There it is, guys. 3 times 7 squared. That would have also been fine. 3 times 7 squared. Okay. Good. All right. Someone else would have just looked at this and be like, okay, that's a perfect square. What's 7 squared again? 7 times 7. Then they would written 49 times 3 straight away, not wasting any time, straight to the point. A product of a perfect square and a another number. That is basically the objective of all of this. The product of a perfect square and another number. All right? Another. Okay, last one. 27. Very good. We got Sasha coming in there at number 1, Leshlokhonolo coming in there at numbers 2, and then Mageva coming in there at number 3. 9 times 3. Okay, we've got 27 being 9 times flipping 3. Okay, then from there, guys, that splitting of the numbers can be done mentally. All right, you saw when I did it most, when I split like physically first, and then I wrote the answer. I mean, that's just wasted step. We could just go straight to the point. Okay, let's just also accommodate there. We would have had 3 squared times 3. Okay, now let's go directly, guys. 100 times 3. Now we know in our heads the square root of 100 is what? Then the square root of 3, that stays under the square root. The square root of 100 is a perfect square number, 100. So what's the square root of 100? That gives us what exactly for our first term? The square root of 49 gives us what? Square root of 3 we know stays underneath the square root. Square root of 9 gives us what exactly? 3 obviously stays underneath the square root. So we're going to have all the root 3's underneath the square root. That is a fact for all of these terms. They are all going to exhibit square root of 3 underneath the square root because all these 3's are staying under. What about 100? What is the square root of 100? The square root of 49? The square root of 9? What is the coefficient here? Because we go straight to the point now, guys. No time wasting. No time wasting. No time wasting. Thank you. Here, square root of 100 is 10. Yes. Square root of 49. Okay, thank you guys in the chat. Square root of 9. 49, 7. Square root of 9. 3. Straight to the point, guys. Now we are not wasting any time. Final beautiful answer, guys. The finale answer. What do we now have here? We have what we call like terms. Why do we say we have like terms? We have 1, 2, 3 terms. Root 3, root 3, root 3. That says the terms are the same, are alike. These are like terms, and we've established that based on our knowledge. Okay, then what do we do with like terms? We keep the root as it is. We add and subtract the coefficients. So 10 minus 7 is going to give us 3. Then 3 plus the other 3, as has been said beautifully in the comment section by, let's see who's this. Okay, no name, only a dot. By dot says the answer. Okay, I'm sorry, man. Let me just rewrite this. Is 6 root 3. Okay, the answer is 6 root 3. Okay, are we catching the flow of this? Okay, so most simplistically, when we are doing this problem, this is how we can basically just do it. Okay, more simply. Okay, guys, we need to, as grade 11 learners, to at least show the product of the two numbers. Okay, we can't just go from here to this step. No. You must at least show the product. of the two numbers, because we want to establish that you know the product of the two numbers. Okay, because I can see some people already saying, so I'm just gonna say square root of 300, and look, the calculator gives me 10 root 3. Listen guys, I get that. Okay, the least at least that you can do is that, all right, take this 10, once you've gotten it, square it. What's 10 squared? So that you can know what was inside the bracket. What is 10 squared? Okay, so that you know that previous step. What is 10 squared, guys? 10 squared. At least, because that's your third step. I get you, that's your third step. But what is 10 squared at least? So that you know what the previous step was. It's 100, right? So it means inside you had 100 times 3. Please, man, don't... woman, you get the point, guys. Please, man, please. Initially, dazzle your teachers. Show them that you know the numbers underneath the square root. Don't go directly. The thing is, the memo, when you guys are people that practice past papers, grade 11 past papers, the memo goes directly to this. No, guys, please, let us refrain from going directly to this, from square root of 300 to this. No, let's first reveal the two numbers. So even if you do use your calculator, you say square root of 300 because you don't want to think. You say square root of 300 is what? You get 10 root 3. Please show the previous step. Take this number, square it, because you were dealing with the square root. If maybe it was the cube root of something, then of course you apply the cube root, you get the answer, and then you cube that outside value to get the product of what was there. And you know, so what I'm saying is, please at least show that step. Okay, please show that step. Now I want to come here. If you're doing this using your prime base exponents, you know, 2 squared, that's a perfect square, and 5 squared is a perfect square. Now you can apply the square root to this, that, and this separately. If you apply the square root to 2 squared, the 2 disappears, you get 2. You apply the square root to 3, you get square root 3. You apply the square root to 2, 2 divided by 2, you get 5. So then here, what comes out? 2 times this times that, obviously going to multiply the 2 and the 5, you get 10 root 3. So this is the way that we move whenever we have perfect square exponents inside. You can just move in this way. Apply the root to each base, of course, because you can. The law allows you to, because the relationship between 2, 3, and 5 is multiplication. Apply the square root here, you get 2. Apply the square root there, you get 5. Apply the square root to 3, it keeps the root there, because this is rational, is irrational, it's a surd. Here, minus the 7 squared is 7. The cube root of 3 is cube root of 3. Here, since this is a perfect square, the square root of 3 squared is 3. Then the square root of 3 is square root 3. So then that leaves you with minus, okay, sorry, there was a plus there, minus 7 to the power 3, square root of 3, plus 3 square root of 3. Then you can add those like terms, you get the very same beautiful answer that you got as the previous one. So it's up to you guys which method you want to use. It's up to who? It's up to you. You must flow with the method that is most delightful and pleasing to you. Okay, so this notion of perfect square and another number, if it's a square root, if it's a cube root, if it was a cube root, guys, then it's not perfect square, but it's perfect cube and another number. And so it goes, guys, with the different roots that you would have. Okay, any questions in the chat? Any questions at all? What is the arrow under for? It's to just indicate that I've arrived at my final answer. That's the arrow. The arrow is there to say, I have arrived. I am there. This is my final answer. Okay. Yeah. When students finish a question and they arrive at the final answer, they write a line with an arrow to indicate that this is their final answer. Okay. Okay. All right, guys, so thank you for that. I hope that is clear. Okay, then I just want to expose you to one last concept when it comes. Hi, Sweet Becky. The question is, how long have you been here? Because if you've just joined the live, Sweet Becky, unfortunately, you're not being sweet now. You are being very sour. If you've just joined the live, my dear, then of course. But if you have not just joined the live, my question is, when I finished this question, why didn't you say anything? Because I stopped here. I stopped and then I asked, how do we do this? Does everybody understand? All right. Yeah. Now the thing is, what I'm going to do is, if I re-explain the questions again, I'm going to actually be chowing as much time as I have used, which is basically meaning that me is basically not going anywhere. I'm teaching in circles. All right. Here to learn and have fun. Junior K, what in the world? Here to learn and have fun. Yeah. Where you have 7 root 3 plus 3 root 3, thought you were to add. Becky, this square root of 3, 10 root 3 minus 7 root 3 plus 3 root 3. This root 3 makes all these terms like terms. Sweet Becky, are you with me? 10 root 3 minus 7 root 3 plus 3 root 3. These are 1, 2, 3, all like terms. Why do we say they are like terms, Sweet Becky? It's because the square root of 3, the square root of 3, the square root of 3 fits into the rule or the law that we had just explained here at the beginning, that if in your root for the same root, this is a square root, this is a square root. In other words, the root is the same. Inside there's the same variable. Then we say these are like terms. So what do? We keep what is the same, the root with its variable. So root A would be kept. Then we add or subtract the numbers outside the root. There's a 1 here and there's a 1 there. 1 plus 1 is 2 snoko. 2 root A. Okay? So back to this example here. We have 10 root 3 minus 7 root 3 plus 3 root 3. Okay? This root 3 is common and it is the same. We treat it like we would treat a variable. We treat the root 3 like we would treat a variable in like terms. So this root 3 multiplied with 10, this root 3 multiplied with negative sign, this root 3 multiplied with 3 is regarded, this root 3, as like a variable. So this is like saying 10a minus 7a plus 3a. All right. So we keep the root 3 as it is. Then we add and subtract the coefficients. 10 minus 7, okay, is 3 plus this 3 is going to be equal to 6 outside the root. Then we follow it up with writing the root 3 because we said the root 3 stays that way. Thank you, Abacus. Is it Abacus? Yes, thank you, Abacus. Abacus with Evelyn Legacies. Thank you for the rose and thank you, Sekhamitze, for the ice cream. Okay, so that's how we would take care of that. All right. So, Sweet Peggy, we are good, ne? You got it now. Junior, does board mess apply? Of course it does. But as you apply BODMAS, what does it BODMAS say? Brackets, no brackets. O, roots and exponents. Well, currently your root is root 3, but these are independently multiplied to coefficients. Thank you so much, Sekhamisi, for that. Lighting up the gallery. Thank you so much. You then treat these guys because brackets, O, your roots and exponents, there's nothing you can do with those because they are just there the same. D, division, no division. Multiplication, 10 and root 3 are multiplied. This is multiplied that. This was multiplied. You can't do anything with that. Multiplication. A, addition. Now you have addition and subtraction of like terms because of this rule. So you deal with the addition and subtraction of what? Of the like terms. Because like I said, root A plus root A. So if the root is the same and what is inside the root is the same, we treat those as like terms. But if what is inside the root is not the same, but we have the same root, but what is in the root is not the same, then we say those are unlike terms. We can't add or subtract unlike terms. So in this case, we can though add and subtract like terms. So I need you to take that in, which is why the answer becomes 6 root 3. Okay. Any other question? Benny. If we factor out 3, oh, Benny, same answer. Benny is saying if you factor out 3, which is the common, okay, so you're gonna say square root of 3 is common. You say 10 minus 7 plus 3. You see, there is an objective with factoring out in this situation. The objective is achieved because it leads to a simplification of the answer. Okay, it's the same thing. You are keeping what is common or what is the same, which is the variable, and you are adding or subtracting the coefficients, right? 10 minus 7 is 3 plus 3 is 6. So then your answer is 3 root 3. Okay, I hope that makes sense. So either way, yeah, whether you look at it as like terms or you look at it as taking out a common factor, the answer is fundamentally going to be the same. 6 root 3. Sorry, not 3 root 3, 6 root 3. Why did I say 3 root 3? 6 root 3. So the answer is still going to be this. That's what it's going to be. Because remember, root 3 times 6 is the same thing as 6 times root 3. Multiplication is commutative in mathematics. All right. I think, guys, I'm going to actually hold it right there because I was thinking of going to the next concept, but I need you guys to really spend some time and you need to digest the initial preliminary problems that have to do with surds and roots. I am going to do rationalizing the denominator, not today, but tomorrow. I'm going to save it for then. But for now, I need you guys to digest and take in, these laws in conjunction with what we've just done. And then you must take it upon yourself to go and find other grade 11 type problems around surds and roots. All right. We will look at this concept of rationalizing the denominator tomorrow because it is a concept that is important. That what do we do when we have a root in the denominator that cannot be removed, or such like questions. Of course, this year, okay, let's answer this question. This is not a rationalize the denominator type question. We'll look at other questions that have to do with that. In actual fact, sorry, I'm looking at this question and I'm looking at it wrong. Look at this question. Let's look at this question. It says show that the square root of 9 over the square root of 3 can be written in the form a root b. I repeat, show that the square root of 9 over 3, square root of 3, can be written in the form a root b. Fabulous day, I don't only do grade 11, I do all grades 8, 9, 10, 11, 12, my lead. 8, 9, 10, 11, 12. In this platform, I do grade 11, 10, and 12. I have another platform for Maths is a Game, which is for grade 8 and 9 only. All right. It's also called Maths is a Game. Profile picture is not white, it is green. You can go and check that one out for grade 8s and 9s. Grade 10, I did earlier on this morning. I'll be doing grade 10 again tomorrow. Tomorrow I'll be doing grade 10 again. I believe at 7 a.m. I told grade 10s I'll be going live at 7 a.m. tomorrow morning for them again. We are going to continue with factorization. But the lesson I did with the grade 10s, I'm going to upload after I'm done with this lesson. I'm going to upload the lesson that I did with them onto my YouTube channel, because all the lessons I do here on the live here, I upload them onto the YouTube channel so that people can watch them or rewatch at their own time, at their own pace. And then if they want, they can harass me with questions in the inbox if they have things that they want clarity about. All right. Show that the square root of 9 over the square root of 3, okay, can be written in the form a root b. So in other words, they want you to simplify this thing so that you have the answer in a form where you will have a number outside a certain root and a number inside the root. The number a into b. A is just a general variable to indicate that the answer should have a specific number outside a specific root. So let's come here. They want us to show this, that this can be written as that in this form. The form, all right? It can be written in this form. So let's come here, okay? And let us simplify first this dear fraction. According to what we have here, we come to the law or the rules. We have a square root of a over the square root of b that can be written as a entire root for both of these, because division of roots, if the roots are the same, like square root, we can write both a and the b underneath one root. So we're going to apply that here. Square root of 9 over square root of 3. That will give us 9 over 3. The 9 in the numerator and the 3 in the denominator are underneath the same square root. Then we can simplify what is inside the root. What is 9 divided by 3, guys? 9 divided by 3. 9 divided by 3. 9 divided by 3. Yes, 9 divided by 3 is 3. But that 3 is still underneath what? The square root. So can we then simplify this any further? No. But when you look at the form, no problem, you can ask your nonsensical question, Jochi. You can ask it in the comment section, that's fine. This square root of 3 that you have there as an answer, look at this form, a root b. Is the answer that we have here, is it in this form? Is it in this form? Yes. Okay, I see in the comment section people are saying the a that you would have there is actually 1 that you don't see there. The ever-abiding, invisible God that we serve. They're present, but not visible. All right? But present. We know that. The B stands for the 3 that we see that is inside the root. So can we then say that we have shown that this is written in this form? Definitely. The answer here is showcasing this form. So look at the question. Show that the square root of 9 over the square root of 3 can be written in the form A root B. There's nothing in that. Simply take what we've been given, simplify it as normally as we know how by applying what we have learned as far as the rules of roots and surds are concerned. Then we are able to get directly to the answer. Okay? Okay. I hope that makes sense. Right, so please guys, will squaring 2 roots that are separate in a bracket cancel the root? Example, the square root of 2 plus the square root of 3. Okay, Tochi, very good question. Will squaring 2 roots that are separate cancel the roots? What do we know we ought to apply when we have different numbers underneath the same root? This is like us adding what? We would call these as what? Are these like terms or unlike terms? These are unlike terms. We treat them like unlike terms. There is a plus sign in between. So what would we do? We would open 2 brackets. Okay? And then we would FOIL them. So square root of 2 times square root of 2. I'm sure you guys understand that the square root of 2 times the square root of 2, that will give us what? Underneath the same square root, we have 2 times 2, which is 4. So that's the square root of 4 in a way, right? Which is 2, as you have said, Sekhamets. I really appreciate that. Okay, obviously that will lead us to 2, right? Then the square root of 2, you multiply it with the square root of 3. What does that mean? The square root of 2 times 3. You are putting them underneath the same square root and you are multiplying. Same thing, you take the square root of 3, you multiply it with the square root of 2, you do the same thing. 3 times 2 underneath the same square root. And then lastly, the square root of 3 times the square root of 3 underneath the same square root. You are multiplying 3 and 3, which gives you the square root of 9. Finally, what does that lead you to? 2 plus root 6 plus root 6 plus 3. Make sense? Square root of 4 is 2. Square root of 9 is 3. You add like terms. What's 2 plus 3? That will give you 5. What's root 6 plus root 6? That will give you 2 of what? Of root 6. Done. So beautiful question that you've asked there, Tochi. Very beautiful question. Because these questions are asked commonly underneath the topic of roots and surds in grade 11 for your exponential expressions. Very common question, this one. So you are actually treating this like you have 2 unlike terms inside your bracket. This is comparable to a grade 10 question of a plus b, the whole thing squared. These are also unlike terms, and what we would do is we would open 2 brackets of a plus b and expand and then solve. So that is 100% fine. The question that you have asked is very valid. So let me repeat that one more time. Square root of 2 plus square root of 3. We treat these as what, guys? These are unlike terms. There's a plus sign in between. We can't apply the square root to the first term and the last term directly. As we explained, that is nonsensical to apply the square root to the square root of 2 alone, and then to apply it to the square root of 3 and say that the answer is 4 plus 9, which is 13. Nonsense. Okay? Yeah, you know, better yet, 2 plus 3. Yeah, whatever it is. People say it's 2 plus 3. They apply the square here, they get 2. They apply the square there, they get 3. And then they say 2 plus 3 is 5. And then that's it. No, nonsense. Rubbish. Absolute hogwash. Okay? That's not how we do it. We open 2 brackets because we're respecting the plus sign that exists between the 2 unlike terms. Then we FOIL. We multiply the first and the first. We get the square root underneath 2 multiplied numbers. 2 times 2 underneath the square root is 4. We take the square root of 2, we distribute it to the square root of 3. We multiply underneath the square root the addition of 2 times 3 underneath the square root for square root of 2 times square root of 3. Then we come to the inner terms. We multiply square root of 3 with square root of 2. Positive times a positive is positive. Underneath the square root, we write 3 times 2 because these are the same square root. 3 times 2 underneath them. Then lastly, square root of 3, the last term, times this square root of 3. Positive times a positive is positive. Square root of 3 times square root of 3. Underneath the square root, we say 3 times 3, which is 9. So this is square root of 9. What is the square root of 4? It's 2. Square root of 2 times 3, square root of 6. Square root of 2 times 3 again, 6 under the square root. Square root of 9, get 3. We add like terms. 2 and 3 are like terms. 2 plus 3 is 5. Snoko. Vula maboto. And square root of 6 plus square root of 6. These are like terms. So when we are adding like terms, square root, roots are the same. Variable, variables are the same. Square root, square root are the same. Number are the same where the variable would be. So what do? We keep the root with its number. We add the coefficient 1 plus 1 is what? Snoko. 1 plus 1 is what? Snoko. 1 plus 1 is what? Snoko. One plus 1. We keep the root 6 as it is. We add 1 plus 1 is 2. 2 root 6 is your other term. And that's it. Okay. So that is it, guys. That's how we maneuver through this problem. Okay. Any questions? Any further questions? Okay. I'm going to hold it right there for today then, guys. Thank you so much. Thank you so much. It's approaching 4 o'clock. I need to hold it right there, guys. I need to hold it. Hold it. No what? No what? Hi guys, I need to bounce me now. Otherwise, this will be too much. Maths overload. You know what maths overload is called? Came late today. Remember, you can actually. Oh, no questions. Thank you. You can always check out the video. Okay, check out the video that I did of this lesson, so that you can actually catch up on that, guys. I'll be seeing the grade 12s tonight at 9 p.m. we are starting off with functions. We'll be starting off with functions, reviewing the grade 11 content for functions, and we'll slowly but surely move through functions, grade 11 content, the concepts around the functions for grade 11, grade 12, and then we'll take it one step at a time, moving forward, trying to unpack that syllabus. But guys, please, the grade 11s as well, please do check out all the other videos that I've done of live lessons for grade 11. You'll learn a lot, especially with the basics from grade 8 and 9, with the exponents specifically. Today I was looking at surds and roots, but in previous videos I looked deeply at exponents and we've unpacked. There's even a video there that's 4 hours where it was a long live, because there were so many issues I was seeing with even grade 12 learners that they are having. Basics from grade 11 and 8 and 9 that they were missing completely. So we need to look at these things and make sure that they are fine. So I will have a live lesson for grade 10 at 7. Then I'll have a live lesson for grade 11s at 9. Tomorrow, 7 o'clock, we are having grade 10. 9 o'clock, we are having grade 11. That is the plan, guys. If anything changes, I will let you know. If anything changes. But thank you so much. Have a great one. And please, guys, let us make sure that we are playing maths, because maths is a game, as we all know it. And please, guys, let's lock in. This here is what we are aiming for. To get a percentage of 95 to 100% for maths, it would basically be saying that you are truly achieving GOATism in mathematics, because this is very possible when a learner is locked in and understands fundamental concepts. Thank you so much. Sekhametsi, thank you as well for the you awesomes. Thank you so much, Sekhametsi. You really lit up. You lit up my gift gallery today. I really appreciate you, sir. I had the 3 finger hearts, and you were able to help me reach all 3 of them in this live session. I think it's a first of its kind. Thank you so much. I think you've actually really been helping me a lot with these ones. I really appreciate it. Ma'am. I'm very sorry for that slip. I think I have a problem with, I think I have Peanut's problem with this thing of him and her. In fact, it's basically something that's a problem amongst us, you know, the him and her, she's and hers and all of that. Otherwise, thank you so much. Have a great day, guys. Let me love and leave you, and please practice the maths, practice, and do more problems from your side. Please move to the other side of the book. This side. You want me to move to this side? I was here on this side. You want me to move to this side? Okay, here's the other side. Yeah, guys, this is what's coming up. This is definitely what's coming up. We are coming here, you know. Yeah, we need the and we obviously when we are done with most conceptual problems, then we will go deeper. We'll go deeper. Equations are waiting. Equations and inequalities, exponential equations are waiting. Inequalities are waiting. Nature of roots are waiting. Word problems are waiting. Grade 11, there's so much. Completing the square of an equation, completing the square of an expression. There's so much waiting. Cheers, guys. Have a great one, and thank you. Even grade 12s need to know the fundamental basics there. Even the grade 12s, they need to know all the grade 12s should be knowing how to answer everything. Like, I mean, literally, absolutely everything. Grade 12s, grade 12s should know everything. How to do nature of roots questions, how to do inequalities, how to do exponential equations, how to do everything. Okay, because these are basics for grade 12s. Grade 12 should be like on another level.